In this video, we're going to find approximations for stress and strain in a two-dimensional triangular element now that we know what the shape matrix looks like for a two-dimensional triangular element. Remember when we were looking at a one-dimensional bar, we found our approximation for strain because we knew the definition for strain was the displacement in the x direction, the change in the displacement in the x direction with respect to the x direction, du dx. We wrote or approximated our strain in the x direction as the shape vector n times our displacement vector u. All of our x dependence was in n, so to find our strain in one dimension was just dn dx times u. We defined dn dx as the vector b. To find stress, stress was just strain multiplied by Young's modulus, and that's given to us by Hooke's law. All right. In order to do this for two dimensions, I've left up the form of our shape matrix for our two-dimensional triangular element multiplied by our displacement vector u1, v1, u2, v2, u3, v3. Our individual shape functions have this form where alpha betas and alpha beta 2, alpha beta 3s were defined, and gammas 1, 2, and 3 were defined in the last video. Unfortunately, in two dimensions, strain is no longer a single scalar value. It now has three components. So we now have strain is strain in the x direction, strain in the y direction, and shear strain in the xy direction, defined as du dx, dv dy, and du dy plus du dx. So now we need to find all three components of strain. Let's just look at, see if we can find an approximation for strain in the x direction. To find strain in the x direction, we need to find an approximation for du dx. Du dx is approximately the derivative of, remember, here to find u, I have u1 times n1, u2 by n2, u3 by n3. This is my approximation for u. So I take the derivative with respect to x, but remember, I've made my shape functions such that all my x dependence is in my shape functions. So this is the same as saying the derivative of n1 with respect to x times u1, the derivative of n2 with respect to x times u2, the derivative of n3 with respect to x, u3. Let's take a look at what happens when I take the derivative of n1 with respect to x. This term doesn't have an x in it, nor does the term with the gammas. The only term that has an x in it is this term. When I take the derivative, the x will become a 1. I'll have beta 1 over 2a. The derivative of n1 with respect to x is just beta 1 over 2a. Remember, a stands for the area of my triangle. Likewise, when I take the derivative of n2 and the derivative of n3, I get very similar terms that only have the respective betas. So I can find my strain in the x direction as simply the vector of betas times my displacements u1, u2, and u3. Similarly, I will find that my strain in the y direction is simply the gamma terms times v1, v2, and v3. Similarly, but with a little bit more work, I can also show that the strain, the shear strain in the xy directions can be written as all 6 components of my displacement vector times gamma 1, beta 1, gamma 2, beta 2, gamma 3, beta 3. Remember that these alpha, betas, and gammas are made up of geographic information or geometric information about the locations of each vertex or each node. Giving myself some more room, I'll move these to the top and clear the board. So these now are my 3 components of stress. I can take these 3 equations and write them as a single vector matrix equation. Give yourself a moment to prove to yourself that this matrix times this shape function, this displacement vector, is equivalent to these 3 equations, equaling strain in the x direction, normal strain in the y direction, and shear strain in the xy direction. We call this matrix now our B matrix. Notice that the B matrix is now a matrix, not a vector. It is a 3 by 6. To get strain, I need to multiply it by my displacements. That's a 6 by 1. The inside dimensions are both 6. I will get out a 3 by 1. That is the dimensions I'm expecting because that is my strain vector, which is a 3-row vector. So now I have a relationship for strain in terms of a B matrix times my displacement vector, just like I had a term for strain a B vector times a displacement vector. The only difference now is that instead of a vector, I now have a matrix. Let's see if I can find a relationship for stress. In one dimension, stress was just Young's modulus times strain. Young's modulus is just a material property of the material that the element is made out of. Remember, in a previous lecture, I showed you that we have these D matrices that relate stress to strain. Depending on our model, we will either use this D matrix for plane stress or this D matrix for plane strain. In either case, though, they're a D matrix, a 3 by 3 matrix that relates strain to stress. So I can find my stress by multiplying my strain vector by my D matrix. My strain vector is a 3 by 1. My D matrix, either one, depending on the problem I use, is a 3 by 3. That'll yield a 3 by 1, my stress vector. Normal stress in the x direction, normal stress in the y direction, and shear stress in the xy direction. Notice I could also write stress as my D matrix times my B matrix times my displacement vector. Now that we have stress and strain, or approximations for stress and strain, written in forms of our displacement vector times matrices that we can define, we're ready to start looking for expressions for the total potential energy stored in our system. We'll do that in the next video.